Hi all, in this video we are going to see how to convert an assembly level language code into a object code. So in order to do this, we have an assembler, and the assembler is nothing but a system software program which is mainly used to convert the instructions which are written in the low level assembly level language code into a relocatable machine code or a object code. And these are the basic assembler function. The assembler will convert the mnemonic operation codes into a machine language equivalent or the symbolic operands to the equivalent machine address, and also it will build the machine instruction in the proper format, and it will convert the data constants of the source program into the internal machine representation, and finally it will write the object program and the assembly listing. And there are two types of assembler based on how it generates the instructions. One is the single pass assembler, which will do its work in one scan. Multi-pass assembler, and here it will do the conversion of the assembly to object code using multiple scans. And these are the assembler directive: start, end, byte, word, reserve byte, and the reserve word. And byte will store the one byte. Word will store one word integer constant. And reserve byte and reserve word will reserve the number of bytes and the words respectively. And the start keyword contains the name of the program and the starting address of the program. And the end keyword represents the end of the source code, and also it have the first executable instruction in the program. And how it will be done in a two-pass assembler in the conversion of assembly level language code into an object code. During the first pass, we have the source code in the assembly language, and we have the op table. The op table contains the mnemonics and its corresponding opcode, and we are generating the location counter and the symbol table during the first pass. Using this location counter, symbol table, and the op table, during the second pass, along with the source code, it will generate the corresponding object code. And during the first pass, it will assign the address to all statements inside the location counter, and it also create the symbol table. During the pass 2, using this address and the symbol table information, it will assemble the instructions and perform the processing of all your assembly directive which are not done in the pass 1. Finally, we get the object program. And there are two major data structure involved in the assembler. One is the op table and another one is the symbol table. Op table contain the lookup of the mnemonic operations, and the symbol table contain all the labels and their corresponding memory addresses. And we have something called as location counter, which will be mainly used for the assignment of the addresses to each program instructions and the labels. And this is the example of the opcode table or the operation code table, which containing the mnemonics operations which is used in the assembly language program and its equivalent machine language codes. And symbol table is another data structure which will be used by the assemblers and the compiler to store and manage information about the symbols and its corresponding addresses in the program. And this is an example where we are having the assembly level language code which should be converted into an object code. And this is the opcode which contains the corresponding machine code for each operational code. And here we see the assembly directives. We have start and we have end. So start contains the name of the program followed by the address, starting address. End having the first line of execution of the code. And these are the opcodes of the op table. And we have the reserve word, reserve word, reserve word. These will reserve a word, and then word, it will store a word. And the first pass, during the pass 1, we are trying to create the location counter, that is the address for each instructions and the label. So we have the start and the end. So starting address is 4000 in the hexadecimal format, and the end directive represents the first line to be executed, the label to be executed. So the first instruction to be executed is first. So we have to fill the location counter during the pass 1. So each instruction basically load 3 bytes. So we are having the next instruction is stored in 4003, and the next instruction will be 4006, and the next will be 4009. And now you know after 9 we have 10, 11, 12, but we have the hexadecimal representation A, B, C. So it will be 400C. And after that again we are having 400F because D, E, F. Then after that we are having 10, 11, 12. So we have the addresses 4012. And next instruction also we have 3 bytes. So we have 4015. So now we have the keyword called as reserve word. So reserve word means we have to reserve 2000 words, each word having 3 bytes. So according to this calculation, we have 2000 into 3 is equal to 6000 bytes. So in hexadecimal equivalent representation, we have 1770. So already we are in the location counter 4015. Along with we have to add this 1770. The location is 5785. So we are reserving 2000 words in between this address 4015 to 5785. And the next instruction is 3 bytes. Here we are reserving only one word, so that is 3 bytes. So 5788. And here we are word storing the value of 0. It's not reserving, storing the value of 0. So this also take 3 bytes. So 578B. And reserve word 1 byte, that is 1 word. 1 word means again 3 bytes. So this will be 578E. So this is the thing what we get during the pass 1. So pass 1, based on the opcode instructions, we are specifying addresses for each label and the assembly directives instructions. So now we are moving with the next phase, that is pass 2. So pass 2, we are going to generate the object code. So basically the object code will be having 24 bits. In the 24 bits, the first 8 bits represent the opcode. And next, 1 bit is used to represent whether it is indirect addressing or the direct addressing. And then remaining 15 bits. So 8 bits for opcode, 1 bit for direct or indirect addressing, and then 15 bits used for the specific address representation. So here the 1 represents, if I give this x value is 1 means it is a indirect addressing, and here 0 means it is a direct addressing. So we have totally 24 bits, 8 bits for opcode, 1 bit for address mode, and remaining 15 bits for the address representation. And here you can see almost all have the direct addressing except this having the indirect addressing. So now we can construct the object code. So how we have to construct the object code? For this particular instruction, we have to see what is the opcode value followed by whether it's a direct or indirect address, and then you have to specify the address. So when you see here for the assembly directives, we don't have any object code. So start doesn't have, end doesn't have, reserve word also not have anything, and then reserve word, because these are your directives. So that doesn't having any representation for the object code. So now go with LDX. LDX, the corresponding opcode is 04 and the corresponding operand is 0. So 0 is in the location 5788 and here it is a direct addressing. So I'm just representing 5788. Then LDA, LDA will be 00 and 0 we have the 5788. So 5788. Then add, the corresponding mnemonic opcode is 18 and now the work comes, we have to represent it as an indirect addressing. So here table. So table value is available in 4015. So we are having 4015. So how to represent 4015? So 4 will be represented with 100 and then 0 will be represented with 00. Then 1 will be represented with 001 and then 5 will be represented with. So now you see here totally we are having 15 bits. So the first bit will be used for direct or indirect addressing. So here table comma x is a indirect addressing. So we are going to represent this is 1. So 1100 represents C015. So our opcode is C015. And now ticks having 2C. Then the count having 5785. And then JLT we have 38 and the loop having 4006. And total STA we are having 0. C then total is 578B. And here we are having R sub that is 4C. It doesn't having any operand, so that will be represented with 0. Then we have the word. Word is actually we are storing the value. So that's why the value what is stored is 0. So 0 will be represented in 24 bits. So we have the value is 0000 because everything will be 3 bytes. That's why we have represented with zeros. I hope now we are clear with how we are converting the first pass each label into a location counter and then followed by during the second pass how we have generated the object code using the opcode symbol table and with the location counter. And now we are going to create the final thing, that is our object code file. So before moving to that, we have something called as forward reference. So forward reference is we are referring some label that will be defined later in the program. For example, here I want to refer 0. So 0 is actually available in the line number 11. So if I execute this thing during the pass 1, then only I know the address of 0 is 5788 to enter this opcode here. So if I am not using forward reference, what happened? I enter 04 and I will wait until what will be the address for this 0. Once I come to the line number 11, after that only I know that the address is 5788. So now using the forward reference, it is very easy because during the pass 1 itself, for every symbol we are generating the location address. So easily we are forwardly referring the label which is used before. That's why during the first pass we already created each label with the corresponding address. So using the forward reference, we are referring the label which will be referred later in the program. So now we are going to create our symbol file. The symbol file first contains the header, text and the end. So to start with, we have to start the header. So header is H. To represent the header, it is H, that is column 1, then followed by program name. So to separate everything, we have to use this symbol. So here our program name is sum. This is our program name. Then followed by starting address of the object program. So to separate this, we have to give this, and then followed by we have to give the starting address of our program. Again, we have to use the symbol, and we have to specify the length of the program code in bytes. The length of the program is calculated that the end of the address is 578E. The starting address is 4000. So if you subtract both of the thing, we are getting 178E. So that will be here 178E. And here we are having something. The first all will be basically the instructions, and the next all will be the data. So now we are moving with the next part of our object code, text. So which will be separated. So text. Then starting address of the object code. The starting address we have to give again in 24 bits. So 004000. So here also we have to give in 24 bits. So 2 zeros to be added here. Okay. So starting address. Then followed by length of the object code in the thing. So here how we have to calculate the length of the object code. We have 1, 2, 3, 4, 5, 6, 7. Okay. So totally 7 object codes are there. Each object code taking 6 space. So 7 into 6, you have 42 columns. Or you may have something called as everything 7 object code taking 3 bytes. So that will be 21 bytes. So this 21 bytes I convert to an hexadecimal format. It will be 15. So I am going to represent with the 15 is the length. So here you have a 15. Then how you have to convert 21 bytes to hexadecimal. So 16, you have 1, remainder is 5. So that's why you're having this. So 15, then you put this, then followed by you write all the object code 045788. Then everything will be represented with the space. So 005788. Then 18C015. So like that you write all the 7 object codes which having the object codes of the instruction. Then followed by data, you have the starting address. The starting address you have is 5788. Because we doesn't have any other data in these spaces of 4015 and 5785. So the data is started only with the addresses 5788. So 005788. We have only 3 bytes. So that byte information is the object code. Then finally we are going with end. So E symbol followed by the address of the first executable instruction. The first executable instruction is first which address, which will be again represented with the hexadecimal format. So we are having this. So this is the conversion of the assembly level language into an object code. So you can see here the first part we have did with pass 1. We created the address of the location counter, and pass 2 we have formulated the object code, and finally we have returned the object code in the corresponding format of H, T and E with the instructions. Thank you.